My name is Emma Button, and this presentation is on the project that I spent the semester working on entitled Mapping Vulnerability to Heat in the Twin Cities. Our purpose, based off the goals of Catholic Charities and the Department of Environmental Health, was to identify the communities within the Twin Cities 7-county metro area that are most vulnerable to the mortality and morbidity effects caused by increased temperatures. We used ArcGIS to create a map of vulnerability in the Twin Cities. We defined vulnerability as those most likely to experience heat-related health problems in the event of increased temperatures. We used 3 different components of vulnerability to inform this map: demographic, socioeconomic status, age, race, urban heat island effect, basically access to nature, and access to emergency services, distance to hospital or fire stations. Previous research has shown all of these components to be major contributors to increased vulnerability. The bottom line is which communities will be least adaptable to increased temperatures. As society continues to develop, there is an increased urgency to understand and predict the relationship between heat and health. Research has shown that recent trends in our society, namely an aging population, hotter summers due to climate change, increased urbanization, and as a result, greater energy use, especially in air conditioners, all contribute to exacerbate the health risks associated with heat. The Intergovernmental Panel on Climate Change predicts that the frequency or intensity of heat waves, and thus heat-related morbidity and mortality, will increase as global temperatures continue to rise. Increased temperatures cause mortality by provoking heat strokes and aggravating existing health issues. Increased temperatures contribute to morbidity by impairing human functioning and productivity, as we have all personally experienced. We partnered with Catholic Charities and the Ramsey County Department of Environmental Health, both of whom were interested in data specific to the 7-county metro area surrounding Minneapolis and St. Paul. This map shows the areas that were considered as part of the study area in our maps. So the research question that our project was looking at was, given certain established vulnerability factors, namely community demographics, urban heat island effects, and distance to emergency services, which communities qualify as being at the greatest risk to increased temperatures? The first component to our map was demographic vulnerability. And based on recommendations from Catholic Charities, as well as previous research, we used data from the 2010 Census Bureau to determine the indicators of demographic vulnerability. And those were communities with a high percentage of non-English speaking residents, communities with a high percentage of people who are rent cost burdened, communities with a high percentage of people over the age of 65, high percentages of no high school degree or the equivalent, high percentages of those who are not homeowners, a high median age, and a high percentage of people of color. This is a visual representation of how we used our data to create the map for demographic vulnerability. From the census data, we pulled out the 7 different categories we considered to be indicators of vulnerability. We first converted these from a shapefile to a raster. Once these were converted to a raster, we had to standardize them so that all the values were on the same scale. Some of our categories were originally in percentages, such as the percent of people who had not finished high school, while some were originally in raw numbers, such as median age. We reclassified them all to a scale of 1 to 100. We then used the raster calculator tool to create an equation based off of these categories. And this is the ArcGIS map showing the spectrum of vulnerability within the Twin Cities. The areas shaded in green are areas of low demographic vulnerability, whereas the areas shaded in purple have a very high demographic vulnerability. Most areas of high demographic vulnerability are concentrated within Minneapolis and St. Paul, with very few highly vulnerable communities occurring in the suburbs. The second component to our map was the urban heat island effect, and the urban heat island effect refers to the trend of cities having higher temperatures than the surrounding rural areas. The graph shows this effect by comparing nighttime temperatures of an urban area with that of a rural area. As you can see, the urban temperature is much higher than that of the rural temperatures. This difference is attributed to three main factors which we incorporated into our map. These are the urban materials used in building most of cities, the lack of biomass in cities, and the geographic landscape within a city. The buildings that compromise cities are usually constructed with dark materials that absorb instead of reflect heat. Metal, another significant component of most buildings, has a high heat absorbance, so it absorbs and emits heat more than it reflects it. These types of buildings, along with a high concentration of pavement, are together considered impervious surfaces. This is the map produced using data for impervious surfaces. The darker the shading, the more impervious surfaces are present in that area. We used the areas with high impervious surfaces in our final heat island effect map. Cities tend to have less trees and greenery, which means that less shade is available as a respite from heat and that less evapotranspiration is occurring. Evapotranspiration refers to plants losing water from their leaves, which tends to cool down surrounding areas. So when cities have less biomass, there tends to be less evapotranspiration and thus cooling occurring. This map shows the presence of biomass within the 7-county metro area. The darker green the shading, the more biomass is present in that area. The criteria we used for our final heat island effect map was that there was little biomass present in those areas. We also considered distance from lakes, since lakes tend to moderate temperatures of the surrounding areas and also generate winds that cool down temperatures. This map shows the location of lakes within the study area. For our final map, we used whether or not lakes were present within a community to determine the urban heat island effect. This is how we constructed our model for the urban heat island effect. We used the raster calculator tool to add together the communities that had no lakes, had a low biomass value, and had a high impervious surface value. We weighted the impervious surfaces twice in our calculation because evidence has shown that this has the greatest effect on the urban heat island effect. This is the final map for urban heat island effects in the Twin Cities. The areas in blue are considered to have low vulnerability, while the areas in red have high vulnerability. Again, there is a trend of high vulnerability areas concentrated within the Twin Cities, while areas of low vulnerability typically are occurring in the suburbs. The final piece of our map is the access to emergency services, namely hospitals and fire departments. Using the presence of physical barriers, such as buildings and lakes, as well as distance, we calculated the cost of getting to an emergency service. This value reveals a community's ability within any given area to respond to change. This map shows the location of all emergency services in the study area. We considered emergency services to be fire departments, which are shown in red circles, and hospitals, which are shown by blue circles. We didn't represent police departments in this map because most police are responding from patrols and not police stations. This map shows the ease of movement throughout the 7-county metro area. Ease of movement is displayed as a value known as friction of distance. Friction of distance is calculated based on the presence or absence of physical barriers within a given area. So the areas in darker red in this map have a higher friction, meaning that they are harder to travel through, while the areas that are light red have a low friction, meaning that they are generally easy to travel through. This map of friction is basically saying how hard is it to move from point A to B. This map is based on traveling via vehicle instead of foot travel because people generally, when trying to access an emergency service, are in a car and not on foot. This is the model we used to calculate the final cost of distance to emergency services. We added together emergency services and then added the friction of distance tool to these services to get the final cost distance, or how much does it take to get to an emergency service. Our final map shows the cost distance to emergency services. The map is showing how hard is it for someone in any given area to access emergency services. Areas shaded in blue have the least accessibility, meaning that there it is hardest to get to an emergency service, while areas in yellow have the highest accessibility, meaning there it is the easiest to access emergency services. So, to sum it all up, our final vulnerability model brought together the three maps we made: high demographic vulnerability, high urban heat island effect, and high cost distance to emergency services. This is our final vulnerability map. This represents the communities that, given the three factors we considered, are at the highest risk of heat-related health issues. The darker red, the more vulnerable, while the darker blue, the less vulnerable. Again, this map shows a trend that highly vulnerable communities tend to be clustered around the cities, while the suburbs tend to have less vulnerable communities. The areas in white are uninhabited areas, such as the river, airport, or businesses in the study area. This was the conclusion that we drew after making our maps. There are communities within the Twin Cities, 7-county metro area who are especially vulnerable to heat-related morbidity and mortality. These communities should take priority when considering public health programs or policies. Now, different organizations will have different definitions of vulnerability, and so depending on what your definition of vulnerability is, what types of demographics one is looking at, the location, the income, depending on your definition of vulnerability, the communities will change. And so future research could be, what are some other definitions of vulnerability that we could use when we inform our map? These are the references where we got information for our sources. Here's where data came from that informed our map. And that's the end. Thanks for listening.